researchers and 8 PhD students, and they conduct pioneering research on magnetoelectronics and integrated microelectronics designed for wearable and implantable devices. His research has been funded by major research councils and funding organizations, including the European Commission, EPSRC, Royal Society, and Scottish Funding Council. He is a member of the RSC Young Academy of Scotland and a member of E-Feature Steering Group. He is a member of EPSRC College and also reviews proposals for the Croatian Science Foundation, the Swiss National Science Foundation, and the Royal Society of Switzerland. Professor Heidari is a member of the IEEE Circuits and Systems Society Board of Governors. He's an IEEE Census Council member at large, a senior member of the IEEE and fellow of Higher Education Academy. He's an associate editor for the IEEE Journal of Electromagnetics, RF and Microwaves in Medicine and Biology, and IEEE Access. He's an editor of Elsevier Microelectronics Journal, and he's a guest editor for the IEEE Census Journal and Frontiers in Neuroscience. Dr. Heidari has authored and co-authored over 170 peer-reviewed publications in top-tier journals and conference proceedings, and acts as a reviewer for several journals and conferences. And he's been a recipient of a number of awards, including the 2020 IET Healthcare Technologies Early Career J.A. Lodge Award, 2019 award from the IEEE Census Council as a Young Professional Award, and Rewards for Excellence Prize from the University of Glasgow, and many other awards. So, Professor Heidari, we look forward to your talk. The floor is yours.
Okay, can you hear me?
Yes, sir. You are very much audible.
Okay. Yeah, perfect. So, thank you very much, first of all, for the long introduction. Thank you very much. So, I really thank you, ISSS for this invitation and pleasure to actually give this talk. So it is a pity actually during this year because of the COVID, we are all working remotely from home, and yeah, hope this go ever and we can actually visit India soon again. So today I would like to give my presentation on neural interfacing electronics. So this is the since this lecture actually is a public, I would just introduce our group activity that what we are doing through different projects in our groups on the implantables, and also just a few mentioning about the few works on the wearable electronics that we are doing in our group in Glasgow. So before starting, I would like to introduce University of Glasgow. So University of Glasgow, founded in 1451, is the fourth oldest university in English-speaking world. It is in the top 1% of the world university, 69th in the QS World Ranking, and it's the home place for the several notable alumni, including Adam Smith, Lord Kelvin, James Watt, and 7 Nobel Prize winners, including actually the several things, and also it is the place that for the one UK Prime Minister and Scotland inaugural and current First Minister of the Scotland. So at the University of Glasgow, we have James Watt Non-Fabrication Centre, which is 1,400 square meter clean room run as a pseudo-industrial operation. It has a large number of the process modules, micro and nanofabrications in silicon technology, MEMS, and other different technologies in optoelectronics, piezoelectric, magnetic materials. It can be accessed through, the commercial access through KNT, Kelvin Nanotechnology company that is a spin-out from the University of Glasgow and second highest cited EEE department in the UK after Cambridge. So this is the website that for those that they interested to know more about the James O'Donoghue Fabrication Center, they can see. So it's a also place for the world best, including the smallest electron beam lithography pattern, best layer to layer alignment accuracy, and so on. So I don't go into the detail. So today presentation, I would like to actually make an outline more visual. So I will go through the neural recording and stimulation project that currently we do in our lab. So this is the main subject for the today presentations. Also, I will explain the other project that we have, not about the brain, but we want to record the muscle activity using the magnetic sensors that we call it magnetomyography. And then also mentioned a couple of other wearables applications that like electronic contact lens and also wrist-worn gesture sensing that we have in our group. So first we start with the brain recording, and then we will go for the muscle and then rest. So the question may be asked, that is, how can we interface the brain? So several technologies have been proposed. So this is not the new actually area. So it is something started from 500 years ago, that the human likes to somehow interface, record, and stimulate the brain. So several technologies, as I mentioned, including the electrical, magnetic, optical, acoustic, and so acoustic or ultrasonic and chemicals, so exist for the interfacing the brain. So in our lab, actually, mainly we are focusing on the electrical. So I will explain through our Hermes project that in the following slide we will explain. And also we recently started to focus on the optical, that we call it optogenetics, that we have a couple of fellowship proposals through our lab. We will introduce this project also. For the recording, actually, so far there are many technologies that can have different resolutions. It can be variables. Here, this shows the number of the neurons, or we call it resolutions, that start from EEG, E-coach, neural probes, that where we are focusing around 100 to 10,000 neurons, and also we have a cellular probes. So they can be placed implantables like neural probes, or they can be EEG, for example, electroencephalography, that can be on the scales. So these, all of them, depending on the applications, we can use the different type of the interface for the actually recording the brain activity. So the graph below actually shows the temporal versus the temporal span versus the resolution of these different technologies. And as you can see, the what we go to the implantables, we want to increase the spatial resolution that we can record. And here the green one is our focus, which is the implantable neural electrodes or neural probes. This figure also shows that in the couple of past decades, the number of the publication on these applications are exponentially increasing. So this research becomes more and more interesting, and as you can see, many activity so that comes up. So the one I can mention about the Neuralink is a company that uh, initiated by Elon Musk, and so that one, made a lot of actually interesting advertisement in this area. So as a first project, I would like to introduce our Hermes project. So Hermes stands for Hybrid Enhanced Regenerative Medicine Systems. So we call it Hermes. So which is a European project funded by European Commission, and includes 12 European partners from different countries in the Europe. So University of Glasgow as one of the partner in this project, we are working on the nanofabrication and nanotechnology that can make the neural probe flexible and a polymer-based electrode. So I will explain the details in the following. But the total concept of the project is to actually integrate the tissue engineering that so a lot of there are a lot of activity, there are a lot of research, or they are focused only on the tissue engineering. So this can actually, by using the neural plasticity, it make a highly flexible and will make a flexible tissue engineering, but unpredictable structure and function that can offer. On the other side, using the electronics and nanotechnology, we can have a neuroprosthetics, which they can actually make a predictable and predictable function and unflexible structure. So by combining these two, we so both tissue engineering and neural engineering. So we are working on these combinations to have a one predictable and also flexible structure for the neuroprosthetics. So if we want to have a look at the background of the brain regenerations, so they are, as you can see here, so they are aberrant. So they want to bring this project, we want to bring the brain regenerations to a control brain regeneration. So in that way, we can make a aberrant brain rewiring to a control brain rewiring. And so for the structure and function, we can control them. And for reinforcement of the pathological brain activity, we can make it a prevention of the pathological brain activities. So this is why we need to have a control brain regenerations. And we are adding the 3 items by combining the tissue engineering for rebuilding, neural engineering for emulate and integrate, and also artificial intelligence for understanding and control. So this figure actually shows the whole when brain damage and dysfunctions happening. So for example, such as the epilepsy. So the core concept is to make the rebuilding function, interaction, integration, and adoption. So all of these using the different building blocks that a different partner in this project, we are addressing the tissue engineering, neural engineering for the bridge, and then control by artificial intelligence. So if we want just quickly have a look at what is the concept of the tissue engineering. Hermes will use the hippocampal organoids as a replacement for the damaged actually hippocampus area in the epileptic brain. So this is not just a brain stimulation, in fact. So this will be the tissue engineering that a lot of groups actually, including our partners in Italy, they are working on that. So the second part that it is about the neural engineering, and by making a neuromorphic computing system, in fact. So these are happening by making a CMOS-based, making a CMOS-based neurons, and also using a memristor-based synapse. So to make a neuromorphic computing system, in fact. So this is the hardware that we can combine with the analog interface. So is a CMOS analog interface, and that can be placed as a chip on the probes. So here is a neuromorphic computing system which can be explained here, and we are by putting the tissue organoid that we are having in the tissue engineering, so they can be control the graft that we have. So this is the whole concept of the reconstruction of the global brain dynamics in our Hermes project. So in this project, actually, our University of Glasgow involving in the neural probe fabrications. So I would like here to explain about what is the ideal neural probes. So ideal neural probes are they should be low impedance, so low, for example, low electrode noise. So normally the thermal noise that we have to consider in the such probes. So should minimize the effect of the voltage divider in series with the analog front end chip, so that we are putting on the probe. The behavior should be linear. We should have a large they should have a large compliance range, and also the probe should have a high current density. So especially for stimulations, when we want to have a stimulations in addition to the recording. Also, they have to show the very small DC offset. So that is the noise that normally comes with the wiring, and specifically when we want to have a dynamic electronics with that. So this should be minimized normally by nanofabrication and also by circuit-based techniques. And then about the size, so size is another issue that normally should be smaller, and typically should be smaller than 20 micro in 20 micro, but depends on the applications. For example, in our project, we are focusing to be less than 100 micrometers. So this is the whole idea, and about how ideal neural probe can be. So here also shows the different materials that they have been used in the fabrication process for the neural probes. So I borrow a figure from actually one of my students' paper to show the trends in the neural probes. So here in this figure shows what is the different type of the probes that we have evolutionary trends. So they are in a different shape and material. They can be from very stiff needle-like actually shaft to a soft material base, mesh, or neuron-like electronics. So, for example, in the A, you can see the stiff shank or needle-like neural probe. In the B, we can see the neural probe with the thick fiber and a polymer substrate. Also here, for example, a stretchable probe with serpentine metallic structure, we can see ultra-thin substrate-based probes and ultra-thin polymer-based probe with the soft conductive materials, and then also mesh-like or mesh-based probes that they are exist. So generally, these 6 types are existing for the neural probes in terms of the material and also shape. So they can be used in the different material. So normally silicon, platinum, or other materials. So we will go one by one. Or they can also be soft rigid material, elastic material like PDMS, and also the soft conductor like PSS or doped hydrogens. So if we want to start, to look at the when neural probe started, so that comes back to maybe half a century ago, that it was the metal-based probe. So here it shows that some actually metal-based probes that it was reported in 2007, in 2002, and also 2005. So we can see the size is less than 100 micrometers, but here, for example, are much bigger, and same for the actually others. So this is the different metal-based probes that it can be. However, so a metal base, as their flexibility are restricted, they can actually damage the brain tissue. So they can increase the also make a foreign as a foreign body reaction. They can make damage the brain, in fact. So because of the some benefits of silicon based, so these technology are going to move towards the silicon based neural probe. So in fact, silicon based are very popular because of they are actually can be integrated with the electronic circuits, so with the CMOS chip, because they are we need to combine with the CMOS because of the in fact signal processing and conditioning. So this is the one of the major benefits of the silicon based neural probe. Another benefit is a high density electrode, so can be achieved in a small volume, specifically for the stimulation. So that is another things that why silicon based neural probes are popular. However, there are 2 main disadvantage for silicon based probes. So one is a stiffness or a rigidity. They are rigid, and because of rigidity, they are prone to foreign body reactions. And then the second problem is because we need to make them ultra thin, so they will be very fragile. So they can be easily, break in the brain. So here shows the some examples of the Utah array or Torres arrays and Michigan array, Michigan probes. So they are one of the most famous silicon-based neural probes. So in that regard, and as a part of our Hermes project, in fact, we are studying the different type of the material that can actually address these issues. So my student Eve is working on the different type of the material to see the young modulus of the different material that we have. So we are going to have a polymer base. So because of the some advantage, I will explain why we need to actually going towards the flexibility to the polymer based materials because of the wide advantage of them compared to silicon based and metal based probes. So sorry, as you can see, we need our materials that we are using needs to be very close to the brain Young modulus, which is 1.89 kilopascal. So we have a different material, for example, PDMS, that it is more closer to the brain Young modulus, but there are some issue with the PDMS, for example, biocompatibility issue. So the other cases that we are investigating is, for example, polyimide or parallelency. And we can see from here that silicon is with 179 gigapascal is much far from the flexibility of the brain tissue. And also the bending stiffness is very important, and this based on the shape of the probes, we have to see that where can be near the brain. And we can see the mesh electronics, it's more closer to the brain bending stiffness. However, there are other disadvantage for these techniques. So we can see the polyimide and elastomer where they are the next actually options, and our focus actually is on the polyimide based probes. Another thing that we have to consider also is biointegration. So biointegrations, as you can see here, shows the equivalent circuit for a brain tissue interface. So in the figure A, and we can see that in this figure, in figure B, insulation damage that creates the undesired current pathway. So we can see the by considering the neurons or astrocyte and microglia. So in the C, we can see the influence of the neuroinflammatory reactions, that we can see that there are a lot of astrocytes around our probe. So biointegrations, in fact, is a very important case that we need to study for the fabrication of the probes. As I said, because of these biointegrations issues and problems in the specifically in the silicon base or in a metal base, in a whole stiff probes, we are going to move in the flexible probes. So in fact, by using the polymer-based flexible probes, we are reducing the foreign body response, and this is the something that we are actually working through the Hermes project in the our groups. So what is the advantage and disadvantage of such polymer-based neural probes? So they are flexible, so they can be fabricated with the biocompatible actually materials like polyimide, Parylene C, or SU8. The fabrication of the 3D array by bending the polymer is possible in this type of the probes, and also the integration and biocompatible encapsulation of different technology. So, for example, we can have for our project, we can have a CMOS neurons, so which are the silicon, and also we can integrate the memory store, which are the other technology together. So this different technology can be integrated on the same probes. So, however, there are two disadvantages that should be considered. So, like challenging implantations due to the lack of stiffness, and also bending may or flexibility or bending may reduce the accuracy in targeting brain regions. So this is the two disadvantage. So for the such things in the Hermes project, as I said, different technology that can be integrated. For example, here as in our Hermes project, we are going to integrate the CMOS-based analog front-end with the memory store to make a spiking neural network as our neuromorphic computing system, on the polymeric and flexible substrate. So this is what we are actually going to do in our Hermes project. So there are many other parameters as key parameters also needs to be considered in the fabrication of the probes. So they are actually summarized here. In addition to biointegrations, we have biocompatibility and toxicity. So another thing is the durability. So this is the very important things that we have to consider. Different type of the stimulations. So we discussed about the mechanical flexibility. Another parameters we are actually working about the using the wireless power and data transmissions in these devices. So I will introduce two of the other works that we are working on this technology. And definitely the form factor and miniaturizations are important. Here also shows the failure modes of the different neural devices, that's from implantations time till day, weeks, and months to 1 year that we need to consider. So this was our Hermes project. I would like to also explain about the another project in our group who Dr. Rupam Das leading this through his Marie Curie Fellowship to the vision and a schematic illustration of the VoiceCure project we can see here. So it is a wireless, scalable, and implantable optogenetics. So using the micro LEDs for the optical stimulations for neurological disorder cure. So the high permittivity dielectric metal material as the antenna here introduce a self-track wireless wirelessly powered optogenetic system in this project, in fact. So the wireless scalable implants can transmit biological data to the smartphone or receive selective stimulations or inhibition. So this implant, also another thing that is one of the implant tissue biointegrations is realized through the designing an MRI compatible implant by using flexible biocompatible and polymer, so biocompatible polymer material. So this is the another project in our group. So recently, so these two projects both started. So recently also, Dr. Finlay Walton, Finlay just started a new fellowship in our group. So he is leading a project called Scotland. So the name is quite interesting. So it's for scalable controlled optogenetics treatment implantables for neurological disorders. So this figure actually shows the concept of the project. So in this project, actually, this project is to utilize state-of-the-art optogenetics technology to design, fabricating, and also develop the actually wirelessly controlled and also definitely biocompatible with a technique of the bottom-up, optogenetic systems. So for conducting this project, actually, in addition to some expertise in the neuroscience, nanotechnology, Finlay is working actually with his previous expertise on optical manipulations for the actually implementation of this project. So this is the mainly fabrication of the mitral LEDs that which be actually in conjunction with the other project, Voice Cure project in our group. So this was the just introduction about these three projects running in our group. Also, we are looking at the energy and power technologies. As we said, there are many technologies that exist for the wireless power delivery because we want to have a fully wireless and autonomous device in the brain. So these are can be through the near field or mid field or far field technology. So these three main actually RF technology, or can be through the solar and ultrasound wireless power delivery. So this is the actually main energy technology for the delivering the power to our devices. So here you can see a comparison among this wireless in terms of the range versus the stimulation intensity. And we can see that where photovoltaic, for example, one of my PhD students also working, or ultrasound, and also near field inductive coupling that exist in the RF technology. So also the far field and mid field are here. So this was the whole our activity on brain actually interfacing. So I would like also goes to other projects that is running in our group. It calls implantable magnetomyography for developing the sensors that can be implanted on the brain for recording the muscle activity. So this muscle activity can actually can be recorded or captured using the because, as you know, we have an electric current in our muscles. So this electric, they are actually generating a magnetic field around the fibers, the muscle fibers. And in fact, this is not something new. It comes from the 1972 with the idea to detection of this magnetic field in the muscle. So, however, there are some obstacles that could stop to having a technology that can capture this picotesla resolution magnetic field, because as you know, the magnetic field around us, so as Earth's magnetic field is around 50 micro Tesla. So which is we need a technology that at least 1 millionum, so in range of the picotesla, to detect this this magnetic field, and at the same time cancel the Earth's magnetic field. So for realizing this technology, we are using tunneling magnetoresistive sensors, so or which are the kind of the spintronic sensors, and in fact their structure is 3 layers. So we have a spacer in the middle, pin layer, and the top layer, we call it the free layer, which are in fact reduce or increase the resistance by applying the magnetic field. So this TMR, or tunneling magnetoresistive, comes after giant magnetoresistance idea that got the Nobel Prize in 2007. So seeming my students are running this project, and as you can see, the difference with the conventional EMG compared to them, there are 2 main advantages. So first one is, since it is designed to capture the magnetic field, so it doesn't need any direct contact. So this, of course, will reduce the danger for any reaction because of the body, because of the foreign body reaction, and also, of course, for the damaging the, reducing the damage of the muscle. On the other side, also, magnetic fields has a higher spatial resolution. So in fact, compared to the EMG sensors, they can offer a higher spatial resolutions, that where it can provide an accurate recording compared to the EMG sensors. So here shows where the sensors can be integrated with the CMOS-based circuitry. So shows the CMOS-based circuitry that for the signal processing we have. So also here shows some results and measurements. For example, here shows the action potentials, and also for the magnetic field in range of the picotesla, as you can see, and also the some other results that we put here. So this is the device that it is fabricated in collaboration with INL Portugal, actually, and has a less than 1 nanometer actually thickness of the magnesium oxide spacer that we have used here. So in the next figure, we can see the our experimental setup, and we use the different type of the technology specifically for the double stainless steel tube for the canceling the Earth's magnetic field. And we have used also arrays of the 256 by 256 sensors, because of the this can provide a lower DC offset. So this project actually is running, and we hope to So Siming is going to finish his PhD hopefully next month. So about the implantables, I would like to just quickly introduce the a few other small project that is mainly PhD project in our group on the implantables. So one is about the implantable PV cells. So Jinwei and Kong actually, so Jinwei and Kong are my students. So they are working on this technology toward implanting the PV cells on the skin uh, for supplying the energy that required for this chip. So here is the power conversion units, which is the CMOS based and will be integrated using the CMOS technology to supply uh, uh, the power that required for our sensors or RF transceiver. In this study also we have investigated where is the optimal location for the PV cells, and actually we have published these results through one of the recent papers from Jinwei in Advanced Healthcare Materials. So the last, actually, this is the last implantable work. We are working also on the wireless power data for the smart stents. So the idea is so we are working with our medical schools who are actually funded by British Heart Foundation to developing the new sensors that can be integrated on uh, the stent actually. So this can provide the more information from the vital sign of the blood to to the outside. So here in this project, in fact, we are designing a antenna, a dual band antenna that can be implanted on the stent to provide to send the power and also receive the data from the outside. So Judy is my student that working on this project, and here are some preliminary results that we have actually from this project. So this was the whole implantable project that in my group, but of course neurotechnology and neural interface is not only implantable, but they are also can be wearable. So one of the interesting, so I just quickly mention about the wearable smart contact lens. So using the contact lens, we can access to to the many symptoms that, for example, we can access to the different different disease, such as ocular disease, such as even is a very clean gateway. Eye is a very clean gateway to the brain, and we can find many symptoms for the neurological disease, such as Alzheimer, Parkinson, dementia, using the tear fluids or even eye movement. So the contact lens that we are currently working, so two of my students are mainly working on this idea, Amy and Asfan. So we are developing sensors, energy harvesting, electronics communications to work actually on this project. These can send these informations to a cloud or through the data communications, and so this can be used by medical healthcare. So here also shows a small video that one of the my students Asfand and Xiamping, they used for the eye gesture based game. So that was using the contact lens actually. Yeah. So the last project that I would like to conclude the lecture is about the wearable sensory gesture control. So two of my students, Xiamping and Yuche, they are working on the fusion of the different type of the wearable sensors in a wristband. So this is the one of the papers that published a couple of years ago, and the idea was to integrate the sensors, wearable sensors, with radar-based sensors for the fusion, and using using a machine learning hierarchical SVM, we could actually control different applications, such as wheelchair, for example. So thank you very much, everyone, for listening. I would like to thank you, my group members. So of course, this is all work of the group members, and I acknowledge, I'm thankful for generous support of the University of Glasgow, European Union, EPSRC, and other funding organizations. So thank you very much, everybody, and I would be happy to take any questions.
Yeah. Thank you very much, Professor Hadi. It was very wonderful talk. The questions are in the chat box. If you want, I can read it out, but some of the questions are very lengthy. Yeah, it will be great of you if you can see the questions in the chat box.
Yes, sure.
Yeah.
Okay. So, so one, as far as I know, neurons are generally not photosensitive. So, how do you functionalize them to the photosensitive without damaging or altering? So will the, yeah. So in fact, heating is the one of the big issue for the optogenetics and micro LEDs. So understanding the how much heat can generate, the implantable device is very, very important. So in fact, this is the one of the problem that optogenetics has, and is one of the obstacles. So they are trying to combine it with the other technologies, stimulation technologies, to reduce this problem of the heating, in fact. So the next question is slide 24. I just quickly go there. In the ViceCure project, probably, how the permittivity is measured and how much improved. So permittivity, actually, this is the work that Rupam is doing. So we are using the metamaterials. So currently we are using the commercial substrate, like Roger, for example, substrate. So using how we can improve this one. In fact, using the metamaterials can, because of their actually advantage compared to the others. I think one of the this is one of the interesting research that recently came up for the implantable because of their actually ability for the permittivity. However, this is not something that we are looking for the fabrication, but using the commercial actually substrate, and also the design of the antenna. So the design on of the antenna, and specifically the shape, is very important. So the next question is how efficient flexible polymer-based neural interfacing probe compared to silicon. So of course there are many problem. The one can be the fabrication steps. So this is a very you know, is not mature as a silicon. So because silicon can go to very high density probes, but I mean, this is the future of the you know, the polymer or flexible is the future of the this application, in my opinion, actually. So have you used them in obtaining the signal from brain? So we are through the Hermes project, we are working with our partners for implanting the rat. So we are doing the rat. So of course, the technology is not actually eligible for the ethically eligible for the human or implantation. So we are using the rat for the obtaining the signals. So would you comment on the applications? Yes. So applications, we have application of in fact, you know, epilepsy that we are you know, we are currently doing, but also in another preliminary work, we are working actually for the different other type like Parkinson. So all these implantables are very sensitive to electrical parameters like current and voltage in micro scale, correct? So how the external effects which will induce static electricity noise around the implants are taking care to avoid any damage. Yes, in fact, they are the external effects, especially for the electrostatic, they are really important. So one of the not only electrostatic, but also the actually the damage for the flexibility and this stuff. So we are doing through a different level. For example, you know, this needs extensive simulations, specifically you know, using the some software like COMSOL or HFSS. We are you know, we are doing to predict any for example, any contractions between the wires that we have on the brain, and this is on the probes, and this is where we can expect any defect or any noise actually. And I can see the last the last one, commonly what type of energy harvester do you use in your devices? Mostly implantable device. So we had one project on the PV cells. However, PV cells are not suitable for the brain, definitely. So we are going for the RF electromagnetics and specifically midfield. So this is where our focus is, you know, is. So yeah, so is electromagnetic midfield.
Yeah, there was one question which has been missed out from Dr. Sudhakar. Why stiffness will be prone to foreign body reaction? If stiffness can be tuned as required, it may not be a problem. Can you please comment on this?
Yes. So slide 16.
Yeah.
So I'll just quickly go there here. Yeah. In fact, you know, so the issue is, you know, one simple actually experiment that we can do. We can actually see if we have a, for example, a needle in a I don't know, something like the very soft tissue. Okay, so this is how you know, the brain is moving, correct? So because of this moving, so if we have something stiff, so of course this you know, this damage will be increased. So one simple, you know, things that we can say, you know, is if we have one needle in the tofu, for example, okay, so in a something close to the brain tissue. So or in Indian we say cheese or paneer, yeah. So if you imagine something, you know, very soft, and you have some needle inside, so you can you can easily see the damage compared to something that, some probes that we have the same mechanical actually properties of the tissue. So this is the mainly things that we can imagine.
Okay. Yeah, we have a couple of more minutes of time. If anyone has any questions, you can unmute yourself and ask question. Yeah.
So there is another question, last one,
Yeah.
how to validate model in the test. So we are, yeah, in fact, it's not easy. So we need a collaborator. So we are in fact, we are a technological based group. So we have a technology as a platform. So we don't do the definitely we need collaborators for testing. So we are collaborating through our Hermes project. So that is we are collaborating with Italian